Okay, we'll make a start then, Mark. First of all, welcome everybody to the Astronomical Society of Edinburgh's May meeting. In this virtual world we seem to spend half our lives living in at the moment. Tonight I've got a few comments to make about what's happening, what's coming up. Then we'll have the talk by Professor Franz Muheim from Edinburgh University. The usual routine on questions. If you've got any questions on Zoom, please use the chat and Peter will pick those up at the end. And if you're watching live on YouTube, put them in the comments section and we'll try and pick those up. And once the talk is over and the questions, we have Horst who's going to talk to us about the sky in May. Thank you, Mark. Can you change the slide, Mark? Thank you. First of all, let's we need to celebrate the fact that we've got 5 new members, and we have joining us Mark, Jean, John, Charles, and Gerald. And if you'd like to unmute, I'd like you to welcome these people in the normal way. Thank you. It's nice to keep some things going the way we normally do. And it's great to see that even in this virtual world, people are still joining us, maybe because of the virtual world, I'm not sure. But with membership now at 112, Alan Ellis, our treasurer, was telling me this is the highest number he's aware of for a long, long time, since we've only started counting people who've paid and not some of those who've probably lapsed. And if you're watching on YouTube, you too can join us for the princely sum of £30, unless you're a student or you're past your sell-by date like me, when it's 15. And if you want details on that, then please look at the website. Thank you, Mark. Can we change the slide, Mark, please? Thanks.
Sorry, my
Just,
internet is a bit slow.
Some pointers on the Society News. Provisional annual report. Sean, do you just want to say a word or two on this?
Yes, thank you very much, Andrew. As we communicated to members a couple of weeks ago, we've obviously had to make some unusual provisions to tide us over this period. We would have had our AGM on the first Friday in June, but we've postponed that and the council is remaining in post for the moment. But one of the things we will do is produce a provisional annual report, which we can provide to Oscar, which is the charity regulator here in Scotland. They're perfectly content with that, and members will get a copy of that provisional report. It will remain provisional until we can organise an AGM and actually formally approve it. But I just wanted to let members know that we are making every effort we can to do what we should do until normal service resumes. With that, I'll hand back to Andrew.
Thank you, Sean. We've got quite a lineup of virtual events coming, including a private showing of Residents Above the Clouds, which was a film made with a Spanish director who spent quite a few years within Tenerife, and which the Royal Observatory in Edinburgh took a lead role, including Brian May. We asked the director through Andy Lawrence if we could show this to members online, and he was happy to give his permission. Sadly, for copyright reasons, we can't put that on YouTube. Now, it is nearly 2 hours long, so we may put a slight break in the middle, but you'll be able to see that. In lieu of our AGM, we thought we'd have a virtual pub quiz, so a bit of a members' evening. We'll look for some other events to go alongside of that at the same time. You can drink and eat whatever you wish, and the prizes will be as virtual as the quiz. And it's nice to think that, that given all the hard work that quite a few people are putting into giving us a much more intense program than we'd normally run, that it's been appreciated and the feedback has been very positive. We've just put that one up from Aussie, and we've had similar sentiments from other people. It's much appreciated for those that are putting in a lot of time. Thank you. Mark, next slide, please. Can we change the slide? Thank you.
Sorry, I have. It's very slow.
Right. I will put the slide up at the end, which will you can either take a screenshot of or make some notes, which will again highlight what's coming up. The ROE on Monday have another one of their talks, which I think we usually provide a link to, but I think you have to book in through Eventbrite. The imaging group is on Wednesday. That's getting extremely well attended at the moment. And on Friday, Tosh is giving us a talk. I don't know if anybody saw the words that accompanied its introduction, but I'll read them out. We gave Tosh White mostly a free hand when deciding what to talk about. Something like space news or a topic that interests you, we said. A pretty dangerous thing, you may think. So we asked him for a synopsis of, and this is what we got. I want to set expectations very low, and then I intend to miss them. I find it's best to disappoint rather than overburden people with false badges. And who can forget his last talk on building an observatory where he lost his tape measure and put his wife down the hole to measure the depth. She freed herself before, as he'd forgotten to remove her, before the concrete began to pour. She's understandably reluctant to visit the observatory anymore. Anyway, we may change the description, but it seems unlikely. So come at your own risk, and we can at least guarantee some planetary shaped virtual vegetables from his garden. So it's up to you. Probably a more sedate performance will be by Jim, who's giving his personal reflections on manned spaceflight. And then on the 15th, correct me if I'm wrong, I think this is the HOICAPS programme, which we've had a talk of before, and Derek Frobrick will be coming to talk to us and giving us an update on the progress so far. Thank you, Mark.
Franz, if you'd like to share your screen now.
Yeah, I'm just gonna try, see if that works. Do I get the right screen? Let's see if that works.
Yeah, that works.
That works.
Yeah.
Now let me see if I go full screen, does it work too? Can you see going it back and forth?
Yes.
Okay, then it seems
It's
to
not
work.
in full screen mode, but
No, we have the wrong screen. This is the preview screen. We see the screen, preview screen, not the real screen.
Yeah, it's the presenter screen that's come up. It needs to be swapped.
Where do I do that? Let me
It's
see.
above the screen. There's a swap screen.
That better?
excellent.
Yeah, okay.
Thank you.
Okay, so yeah, should I simply get going, or how does it work?
Yes, sorry. Yes, I am. Please, I expected an introductory slide to come up, but not to worry. Yes, please, Franz, carry on. Thank you.
Okay, good. So it is a pleasure to be here. Yeah, in in lovely South Edinburgh, actually, even if the picture behind me is from the Aletsch Glacier, as I saw it last year. yeah, Carl asked me some time ago to give a talk, and we discussed a bit. Apparently, when I said neutrinos, he immediately jumped on it. So I'm going to give a talk on neutrinos. What are neutrinos? Oh, how do we measure neutrinos? What do we know about neutrinos? Where do they come from, and so on? I'll talk a bit about current and past experiments, and then towards the end about the future. So where do we start? I always say this: we are not the biggest beast on Earth. We are not the fastest one. We don't have the biggest claws. What distinguishes us, and with what we are ruling the world for better or worse, is what we have between our ears. And it goes back to the dawn of humans, when they have been wondering about the stars and how the universe works. And here's a picture which I found of the Milky Way, somewhere in the north of Scotland. Now, modern science works a bit different, in that you make proposals and then you test it by an experiment, and nothing gives an experimenter more pleasure if he finds out that his friend's idea has not worked. But sometimes things come together, and Newton's gravity is one example, when he realized that what made the apple fall from the tree is the same force that makes the Earth revolve around the sun, and now the sun around the center of the Milky Way. What we start now is a quick introduction to the standard model of particle physics. Actually, for neutrinos, you don't really need to know this, but I think it's useful just to set the perspective. We all know there are atoms, and there are nuclei, and in the nuclei you have quarks. In an atom you have protons and neutrons, and they are made up of an up and down quark. And in the atom then you have an electron. And then in the first generation there's already the neutrino, which will be with us for the next good part of an hour. However, the quark model seems to replicate itself. There are 3 more families. Like the second one is these muons, which arrive in cosmic rays. And for the third one, if you want to do top and bottom quarks, which is pretty much my day job, working with bottom quarks, you need a laboratory to make these. Now, how are they held together? And we know there are 4 forces. There is electricity and magnetism, which are combined. And then there's the strong nuclear force, which binds the quarks in the protons and the neutrons, which keeps the nuclei together. But then there is also something like the weak force, which we better know as radioactivity. And, and this is actually rather new. Kelvin didn't know about it, and told the geologists they are wrong when they claimed the Earth has to be older than 50 million years old, which all it could have been due to the electromagnetic potential. And then there is gravity, but we don't talk about gravity in our fields. It's just too weak. So we have the standard model of particle physics. We have these interactions, which are actually mediated by particles, these bosons like the photon. And the local stuff which goes in is obviously Peter Higgs, who more than 50 years ago predicted a mechanism together with others, but he also said there has to be a particle with it, which now bears his name. So these neutrinos, you see, they are like quarks and electrons and muons, so they're also leptons, so they are mass particles. In that sense, they're the same, but that's where it stops. Because I'm going to tell you a crime story now. And the crime story has a beginning, then the plot thickens, and then you wonder who done it. And at the end, you wonder if you have solved it. So let's start at the beginning. The beginning was in the 1930s early 1930 and 20, when people were measuring beta decay. So they called these particles betas. They didn't know yet they were electrons. Or what was in the nuclei. But they found a spectrum like the one, I think you should be seeing my mouse here, like the one which is continuous. However, the expectation was that it was a two-body decay, so they should have seen a line. And this confused a lot. And people know, as experienced as Bohr, were wondering if conservation of energy was not a fundamental thing, but like we now know about entropy, just a statistical game. Pauli thought about a bit harder, and he wrote this letter, which is where it started. Liebe radioaktive Damen und Herren. So, dear radioactive ladies and gentlemen, I've hit upon a desperate remedy to save the conservation of energy. That there could exist neutrons, that in beta decay, a neutron is emitted in addition to the electron. Unfortunately, I cannot appear in Tübingen, where there was a meeting personally, because I'm indispensable here in Zurich because of what is known as the polyball. So he had, Pauli had married shortly before, and his wife told him, you have to come to the ball. So he couldn't go to that meeting. This is where the neutron, or as Pauli called it, was postulated. The name neutrino, which is Italian for small neutrino, was coined by Fermi when he formulated the theory of beta decay in 1933, because meanwhile, Chadwick had discovered what is now the neutron. So basically, now a neutron or any beta decay is a three-body decay and the spectrum works. However, neutrinos can be lots of fun. This is a screenshot I took from a TEDx lecture on life lessons from mysterious neutrinos. And you see, they are made in the Big Bang, in the center of the Earth, in power plants, in the sun, in nearby and faraway galaxies. And we'll encounter them all. But neutrinos have zero charge. They only interact weak. And this makes them very special, because when we say they interact, we tremendously exaggerate. They don't interact. A neutrino can go through 60 light years of water without interacting. Pauli, who was quite acerbic, was also acerbic against himself and said, gee, I've done a terrible thing. I've postulated a particle that cannot be detected. It's also must be very light and in the Fermi theory massless. However, there are lots of them. The neutrinos from the Big Bang are actually the most abundant matter particles in the universe. Up to some statistical factor, we see as many neutrons as we see photons, about 300 million in a cubic meter, whereas you find 5 measly atoms. The sun is a fusion reactor. Each second, 100 billion neutrinos pass through each square centimeter of us. Of these, only a handful will actually react with us during our lifetime. Now, what happened then? Well, yeah, people tried. I mean, we are physicists. If it's impossible, we'll try it. Cowens and Rains were the ones who were successful. Their original plan was to use one of the nuclear bomb tests in the 50s, but they realized it had background problems apart from the logistics, and then settled on reactors, which also have a sizable flux, about 10 to the 20 per second. And on the right, you see the picture of the two guys in front of their apparatus. the schematic of the apparatus is below here. And the process is what is called an inverse beta decay, where what we know now, an antineutrino comes and hits off a proton, turns it into a neutron, and emits a positron. This positron then annihilates with an atomic electron. The detector with 400 liters of liquid scintillator, so water and cadmium chloride. And with the chloride, you got a delayed coincidence signal with the neutron. So you had a coincidence of the signal from the positron and the neutron, which basically made the experiment real, because you could beat down the background. Remember this, because it comes back at the end. So on 14th June 56, Rines and Cowan sent a telegram, which you see on the right-hand side, informing Pauli that they definitely detected neutrinos from fission fragments by observing inverse beta decay of protons. To which Pauli wrote himself below, "Thanks for message. Everything comes to him who knows how to wait." In hindsight, it was quite fortunate, because if I recall, Pauli was already ill at the time and he died about 2 years later. So, plot thickens. We know a neutrino is a neutrino, is it? Well, we know these neutrinos, they started popping up in interactions in the 60s, together with the electrons, but the muons, which were just the heavier sisters or brothers of electrons by a factor of 200, they produce neutrinos too. And the question was, are these the same neutrino? Well, turns out they are not, because in 62, there was an experiment with a pion beam, which produces muons and neutrinos. And this then was hit into a target, and then it produced muons again, but it never produced an electron. Same experiment was done with pi minuses and antimuons, same result. The people who did it were Lederman, Schwartz, and Steinberger, and they got the Nobel Prize in 98 for it. So we also have a muon neutrino. So there seem to be 2 neutrinos. And the standard model clearly said there has to be a third one, which was detected by an experiment called Donut in what we call a beam dump experiment. So the beam was dumped in concrete, and you look up what comes out on the back side, and on the back side, they had an emulsion target. And when they developed the emulsions, okay, there was some triggering and electronics, they found these short stubs of tracks, couple millimeters, and then a kink, which is a tau particle decaying into a pion or a muon. So, and if you then don't have background, you see that. On we go. The sun is a fusion reactor. I've already told you about the statistics. Ray Davis started doing an experiment in the Homestake mine in South Dakota, where he had 400,000 liters of cleaning fluid. He started measuring the neutrinos from the sun with 37 chlorine in the cleaning fluid, which then produces 37 argon, which is an inert gas, and an electron. And for me, I mean, I'm a physicist. Ray Davis was a chemist by training, because what he did is every couple of weeks or 3 weeks, he took the 400,000 liters, so 100,000 gallons of cleaning fluid, and flushed out a handful of argon atoms. That's a feat. And he started measuring it, and he measured it from 97 to 94. And the prediction was 8 in some units, and he measured 2.5. So he came up a factor 3 short. There's a break when the experiment didn't run in 86 or so. I actually remember going to one of my first conferences and meeting Ray Davis. And after the session, some of us talked. And there he said something which I remember to the day. You know, when you do a neutrino experiment, you have to be patient. You have to keep on and not just do a quick and dirty experiment for 10 or 15 years. So, and he had patience. So, yeah, what happened? Oh, what's the problem? Did Ray Davies screw up in the sense, oh, maybe he wasn't as good as extracting a handful of argon atoms as he thought? His sidekick was John Bacall, who calculated the model, the rate of how many neutrinos. And here is the neutrino spectrum. Here is this 100 billion of if you know how the sun works, they are proton cycles. But the ones which the Davis experiment was sensitive were essentially these 8 boron neutrinos. And they had a very high temperature sensitivity. And I remember John Bacall himself at the conference saying, at the time, I didn't believe that my model was correct. So was it this? And the order is maybe random, but actually most people thought Davis was wrong or Bacall was wrong. Everyone knew the neutrinos were correct because they are simple models, simply to calculate in the standard model on the back of the envelope. So other experiments started going on. I'm taking one which was actually built to find proton decay, which they never found, but they found a few other things. It was called Kamiokande. And I'm skipping a generation and already give you the results from Super Kamiokande, which was the successor, which started in '97, which is 50 kilotons of water with 11,000 phototubes. So each one of these is a phototube, and each one is 20 inches. So they are huge. And they started the data taking. The process is basically an electron neutrino comes in, produces an electron, produces Cherenkov light, which you detect. Now, what's the worst thing which could happen to such a detector? And in a lecture, I would now pause and ask. I'm going to give you the answer. On 12th of November 2001, there was, shortly after this picture was taken, one of the tubes imploded, but it was filled again to 2/3. So what happens if one of those tubes implodes? Well, the neighboring got a shockwave and imploded, and so on. And every tube underwater imploded, so about 60%. Basically caused the day of national mourning in Japan. Luckily, Japan is a well-functioning economy and pride is everything. So they immediately had a plan to re-equip. And over the next, by 2008 or 9, it was fully equipped again. But there was enough there to do good results. So they measured this process, and in electric scattering, the direction of the neutrino is preserved. And so what you can see here is that you can see the sun with neutrinos, essentially. What is plotted is the angle, actually the cosine of the angle between the direction where the neutrino comes and the sun. And they clearly come from the sun. You count them, you measure, and they're measured about half of the expected rate. So that meant Ray Davies was correct. They are correct. It's not the measurement. The puzzle was only solved in 2002 or so, when another experiment called SNOW, Sudbury Neutrino Observatory in Ontario, Canada, started operating. They used 1,000 tons of heavy water. For this, they had to go to the Canadian military and say, can you loan us all your heavy water? Which the Canadians gracefully did. They had to sign some paper, probably not in ink, probably in blood, but the experiment got done. And you see an artistic sketch. So it's basically a big ball of heavy water inside water. The difference is that with the heavy water, this measurement, this detector is not only sensitive to this elastic scattering we have here, but also on the charge current interaction, but also to neutral currents, where each neutrino interacts. So if you're a physicist, so where a Z is exchanged instead of where a W is exchanged. And they saw this, you still see the electric scattering, but you also see this neutral current. And they measured that about 31% of the electrons, of the neutrinos, the solar electron neutrinos, arrive as electron neutrinos. But if you take these and you scale with efficiencies and everything, they saw exactly as many as you want. You can look at it in this plot. Basically, the blue band is the total, and the blue band is the sum of the two axes, and it's anti-diagonal, so it always adds up to 5, which in these units of SNU is what they expected. Whereas the red vertical line is the electron neutrino, where they only see 1.7 or something, so a factor of 3 too short. So the solar neutrino puzzle is in a way solved. Oh, it's not a measurement problem, so Ray Davis was on the right track and John Bacall was on the right track. And Ray Davis at the end got a prize for it. John unfortunately missed out. Yeah, as in a good crime story, if you eliminate everything which is possible, only the impossible remains. It has to be these bloody neutrinos. And I'm obviously a bit taking a license with the timing. I don't know, I hope you don't see this. What happened here? Okay. Oh, now I'm getting, now I lost, let me see. Am I back? Yeah, looks like. So basically, cosmic rays produce neutrinos. So when protons hit the upper atmosphere, they produce particles called pions, which then produce muons together with a neutrino. The muons themselves produce electrons together with an electron neutrino and a muon neutrino. So if you do the counting, you expect 2 muon neutrino for each electron neutrino. And if you now go in a detector and these neutrinos do elastic scattering, so muon neutrino produce muons, electron neutrino produce electrons. You then have muons or electrons which will travel rather fast with a speed of which is larger than the speed of light in that medium, which is c/n. And you can see this is a typical muon event because the muon goes more or less straight. It produces a clean ring, whereas the electron starts to shower. So you get a fuzzy ring. So first they were looking by eye, but basically if you can teach your computer to get the difference between this ring and this ring, you can understand if it's a muon or an electron. And the Cherenkov light is basically this this boom of light. It's the same mass as a sonic boom. It's the light you see, the blue light you see in a nuclear reactor, amongst other things. So they started doing these measurements in the 80s, and already in the early 90s, there were indications that there were too few of these muon neutrinos. The result from Super K in '98, shortly after switching on, does the following. You again measure, Super Kamikande is here, you measure the neutrino as a function of the angle. And so the zenith angle, so cosine equals 1 is from above, and cosine equals -1 is from below. So these are neutrinos which come through all through the Earth because for neutrino, the Earth is invisible. They'll just go through. And what they observed was that for the electrons, they observed exactly what they expected. Whereas for the muons, they observed fewer, but at the zenith, so from above, where the distance is short, they observed what they expected. And the ones which came all the way through the Earth, about half of them had disappeared. So it seems now that the neutrinos disappear on the way. So neutrinos are oscillating. So this is was the first incontrovertible evidence of that neutrinos oscillate, because they are correct here and then they suddenly disappear. What do they change to? Could it be tau neutrinos? Well, we now know neutrinos are different. One thing which I'm not going to derive, but you have to trust me on that, is if neutrinos oscillate, their masses cannot be zero. So the mantra, neutrinos are massless, was simply wrong. The mass is also something, and we'll come back to it. It's not like the mass of other particles or the one which is linked to Peter's boson. So neutrinos are possible only with non-zero mass. And then they oscillate. And so I played for 10 minutes, tried to make a GIF and failed. But so I did this. And so these neutrinos oscillate into each other. This is exactly what's happening. And you can already see, it will now depend what is the frequency. And we'll come to this probably soon. So let's try to understand this qualitatively. Basically, a neutrino is also a wave, because each particle is a wave. And an electron neutrino is actually a combination of the three neutrinos mu1, mu2, mu3, which are what we call the mass eigenstates. So the neutrinos have different masses. And when they travel, I've already had mu1 travel. Now I let mu2 go. They have slightly different speed because the speed depends on their mass. So they oscillate at different frequencies, and you all know what happens. If you overlay two waves with a very similar frequency, you get a beat. And it's exactly this speed. It's very simple quantum mechanics. Not that we understand quantum mechanics, but this is what happens. The neutrino flavors change back and forth as the neutrinos traverse distances from the sun to here, about a third, through the Earth for the cosmic ray neutrinos, about a half, so they oscillate away. So I'm going to show you one formula during this talk. I've always been told if I showed formulas in talk, the audience will leave or go to sleep. But I decided, bear with me, because it sums it up quite nicely. What is the probability on these neutrino oscillations? And it depends on very few parameters. One is what we call the mixing angle, which is how likely it is to go from one into the other. And here we only look at two components. For three, you just go from 2 to 3. And then the frequency, which if you understand a bit of math, is in this term inside the sign. The frequency basically depends on the distance you travel and the energy of the neutrino, in fact, of the ratio. And if you take convenient units, you get a factor of 1.27 in front of it. So for atmospheric neutrinos, we know that they are mainly a mixture of 2 and 3, and L over E is about 500 kilometers per GeV, distance of the Earth over the few GeV of their energies. And you measure delta M, and you are here. So delta M, and it goes with delta M squared. So it's about 10 to minus 3 eV squared, or if you take the square root, it looks like the mass difference is about 30 milli-electron volts. You could do the same game with solar neutrinos. And there the distances are larger and the energies are lower, and you get a larger number here. And their mass difference is also 10 to the minus 5. So it's only a few milli-electron volts actual mass. So the interesting thing would now to be not only to measure disappearance, but could you measure appearance? And there are many ways it has been done. I'm picking out a couple. One is the electron neutrino appearance in a particle physics experiment. It has also been done with reactor antineutrinos. The T2K experiment uses a neutrino beam produced by what is we call J-Park in Tsukuba at the what is the east coast of Japan, travels 300 kilometers westward through Japan at Super Kamiokande as their far detector. They also had an ear detector to sort out the systematics and the backgrounds. And alas, they measured about 28 electron neutrino events. This is one of their candidates here. They have an energy spectrum, and it fits well with their expectation. And from this, they can measure the mixing angle, θ13, for example. The tau neutrino appearance measurement was done at Opera. Opera was one of those emulsion experiments, and they used the neutrino beam from CERN in Geneva to Gran Sasso in the Apennine Mountains near Rome, 730 kilometers away. And there, the mu neutrino could oscillate into a tau neutrino. And what you actually see is a picture of the apparatus. So there's electronics, but there are lots of emulsions which they had to develop. And this is their first neutrinos, their first tau neutrino. You see this, here is where a neutrino hit a nuclear interaction. So tracks go off. And there is this guy which only travels 1.3 millimeter and then produces another track which goes into another direction, and then some neutral stuff which goes here to conserve momentum. Therefore, this is, they have little backgrounds. This is a tau neutrino. I think they measured about 6. Given that the experiment cost about 150 million, it was quite steep per tau neutrino, but it's important. So this was good. So to sum up, the masses of the neutrinos. What we don't know yet, they have 3 masses, but are they aligned like this? I.e., is M3 about 30 or 24 milli-electron volts? This is this is again the square, or and this is the small mass difference, or is it the other way around? And this goes under normal hierarchy, and this goes under inverted mass hierarchy. So can we measure the neutrino mass directly? Well, we can try, and people have tried. And when I entered the field, there was a positive measurement that a Russian experiment claimed it was 35 electron volts, and but it has gone down. Basically, you look at the endpoint of a beta decay spectrum. The last one to do is this Katrin experiment. This is the size of a house. And you see it here in reality with the person suited up inside. I have a picture somewhere how it went somewhere during transport in a village where it got a bit tight. This is the measurement of their spectrum, and basically they have to measure that endpoint extremely well, because if the neutrino would have mass, this would shift ever so slightly to the left. So it didn't. And the measurement, their first result was announced last September, and this greatly reduced the limit, and it's now 1.1 electron volt. So this is the best direct measurement we have so far. So I could stop now because we've solved the story. However, if you look apart from the Catherine experiment, apart from the Catherine experiment, most of these measurements are 15 years old or more. So the question is there more to neutrinos? Well, I already told you one thing, namely this hierarchy. There is another one. You might have heard about Majorana. Majorana was a famous physicist who disappeared, was last seen in the 30s on a boat, and we don't know if he committed suicide or if there was something more sinister to it. But because the neutrino is neutral, there is no fundamental law which forbids it to be its own antiparticle. So could the neutrino also be the antineutrino? And the way to check this is conceptually rather simple, because there are some decays, some nuclei, which not only do a beta decay, like an electron and an antineutrino, but do a second one with an electron and an antineutrino. And now, if the neutrino would be its own antiparticle, this one could go being absorbed by the other, where it's a neutrino, and you could see this decay without neutrinos. So you would see a monoenergetic line instead of a spectrum. I can tell you that neutrinoless double beta decay has not been observed. Double beta decay has been observed, and the lifetimes are in the order of 10 to 20 years and longer. Kamland has the best limit. Gerda is another one which put out a limit last year. And so here you see the limits depend on the calculation, because you need to do what we call the matrix element to get from the measurement into the nuclear physics, which has about a factor 2 uncertainty here. But basically, you get a band on the mass limit, and you see it's a factor 10 better than the direct limit. Cosmology also tells you about limits, because neutrinos used to be dark matter candidates. Now they are ruled out. But if they are too heavy, you would see them. They would be seen by things like Planck. And depending on how much model assumption you do, they get limits of similar numbers, like 120 electron volts or a bit higher. As particle physicists, we are a bit cautious about these numbers, but still they are. But even, and then you have the Catherine experiment here. But even if you take everything, you have this region for the normal ordering, which is fine. But for the inverted hierarchy, the next generation double beta decay experiment might get it. So neutrinos open up new frontiers. So what is the neutrino mass hierarchy? We asked. Are neutrinos their own antiparticles? There's another thing I have to tell you about. Have you ever wondered why the universe looks like this, Hubble deep field, and not like that? If you are a simple-minded physicist like me, the one on the right-hand side is much more natural, because we knew at the Big Bang everything was created equally, and everything should have annihilated, and all there would be left is the 3 Kelvin background radiation, nothing else. But because the protons and antiprotons annihilated everything within the first millisecond, how could the structure have been made? How can the universe be as it is, including us? How can we observe it? This matter-antimatter asymmetry is fundamental. these are created in pairs, and they should exist in equal amount. On the right top, you see the discovery of the positron in 1932, where you have this thing going through a plane and then bending more. And since you know the charge, it looked like an electron, except it bent the wrong way, so it was positively charged. Huh? We have matter dominance about 1 in a billion. If they annihilate each other, you actually generate huge amounts of energy, about 1,000 times of fission or fusion, because all of E equals mc squared would be annihilated. So we have looked. It's an honest question. Couldn't there be antimatter galaxies out there? The answer is actually no, because even the 5 atoms in free space would be enough to produce 511 kV lines at the boundary region, which we would see. Antimatter are used every day. Whoever had the unfortunate unfortunate enough to undergo a PET scan, that's a positron emitted from a radionuclide. At CERN, we've produced anti-hydrogen atoms. At Fermilab, the storage ring had about a nanogram of antiprotons. But if you read Angels and Demons, and you wondered about this X33 transporter, which took Tom Hanks from Boston to Geneva in an hour, I have to disappoint. I stand in line with everyone else with EasyJet, assuming they will ever fly again. Yeah, they still owe me flights too, so we are all in good company. Okay, so one more thing about the physics of neutrinos. Neutrinos undergo the weak interaction, and the weak interaction has a chirality. It's left-handed. So the neutrino spins. It has its spin. It's spin 1/2, and if you turn it into a chirality, it's left-handed. If you then put it into a mirror, you get a right-handed neutrino, but that doesn't exist. If you make a neutrino, an antineutrino out of it, which is called charge conjugation, you get a left-handed antineutrino. Doesn't exist either. However, if you do both, you get a right-handed antineutrino, and that exists. And so I did this because of the 2 letters CP. This is charge conjugation and parity. So neutrinos seem to undergo or obey charge parity or CP symmetry. Why is this important? Because of BAU, the baryon asymmetry in the universe. I repeat that in the Big Bang, there was a tiny asymmetry created between particles and antiparticles. Sakharov wrote down that there are 3 requirements for this to happen. One is CP violation, which is the difference in the behavior between particles and antiparticles. And there are 2 more. One is the violation of baryon number, and one is an epoch of non-thermal equilibrium. Otherwise, it would wash out. So something like inflation could do. Now, leptogenesis is a theory where CP violation appears in neutrinos and then explains the BAU, because if CP is if neutrinos have CP violation, you then immediately produce baryon baryon number asymmetry as well. So in a way, the proton will have to decay. So another thing to add: why is there so much matter and almost no antimatter, which could be neutrinos? Actually, this is the reason why I'm in neutrino mainly, because my previous career, or my still ongoing career, is on measuring CP violation in quarks. Now, to do this, we're going to build the largest ever neutrino experiment, which is called DUNE LBNF at Fermilab. It's the largest ever neutrino experiment being built. You need a lot of friends. It's a truly global project. You need lots of money. And you have, the idea is we want to measure this CP violation in neutrinos because this is the next prize. And so you see, this is Fermilab. This is, now it went too fast. This is Sanford Underground Research Facility, or SURF, aptly named, which is in South Dakota. There's a mine underneath, which actually is the same mine where Ray Davis did his solar neutrino experiments in the 60s. And you see here this graphic, how the neutrinos, which were the mu neutrinos, would oscillate mainly into tau neutrinos on their 1,300 kilometers to South Dakota. The detector would be 4 such modules comparable to the size of super tankers or a small not quite a football field, but 2/3 the length of a football field. Each one having 17 tons of liquid argon. So it's going to be the largest liquid argon dure, and that's 2 miles underground. Let me see if that works. So here you see a nice movie illustrating this. This is the famous Wilson building at Fermilab, where these ideas get created over coffee in the minds of physicists. And here's where you start. It all starts with an accelerator. You accelerate, which make the beams faster. You then put them in an accelerator complex, then in another one. This is the ones at Fermilab. At CERN, we have similar ones. And then you extract the beam and goes slightly downward and produces neutrinos here. These neutrinos and here. And you have a near detector here, and you see it produces data, which you record. And then you go through the Earth. The neutrinos laugh about the matter and arrive in South Dakota with speed of light. And here we have these modules, and they record events. And because the interactions are so small, you have to have such big models that at least a few neutrinos interact. Actually, most events in liquid argon are actually going to be background from argon-39, which is one of the argon isotopes. But here you see how this is done. Then the data get shipped all across the Earth and being analyzed. It is a truly global project. CERN is part of it, and we built at CERN what is called ProtoDune, which are this is about 10 by 10 by 10 cube. We built 2 of those prototype. This is new. 4 years ago, this was a football field. But if you give someone like Marzio Nessi, who built Atlas, a check where he can put in a number, things like this happen. This is the cryostat. And I have another movie on how this liquid argon time projection chamber works. So the neutrino come in, most of them do nothing, but if one hits a proton, it can produce either a muon or an electron, which then produces tracks. And the time projection chamber, which is the liquid argon, these electrons get collected at the end And so you produce 3D images. And funny enough, we use imaging theory to reconstruct this. These are real events from protodune, and you see most come from above, and that's because they are cosmic rays. There's a similar experiment being built in Japan. It's called hyper Kamiokande. So if you ever ask what's better than super, it's clearly hyper. And it's about 5 times the size. And they want to make 2 of them. Let's see. Sorry. And they will use a 1.3 megawatt proton beam from J-Park. In a way, they are competitor, but the experiment of simulation is so big, you better want to be sure. But they're also complementary because the technologies are different. For example, for solar neutrinos or supernova neutrinos, hyper-K is mainly sensitive to antineutrinos, where dune is both. So, since I'm invited by the Astronomical Society, I did some homework on what we can learn from astronomy about neutrinos, or can astronomy learn from neutrinos? And I have to go back quite a bit. In 1987, we had supernova SN 97A in the Large Magellanic Cloud. But the theory is what happens in this collapse is, at the end, a proton and an electron fuse to a neutron and a neutrino. So actually, almost all of the energy is dissipated as neutrino in such a collapse. And this is the one from the Large Magellanic Cloud. And I was a graduate student then when they found these 17 neutrinos. One thing which is unbelievable in hindsight, they didn't know the timing of these neutrinos because they didn't have GPS or other watches. So they had to go and look it up. But I think now we agree they came about 2-3 hours before the visible. So in June, we will see a supernova if it goes off in the Milky Way, and the canonical expectation is 1 per 30 years. So we are due one. We just hope it only goes off when we are live. And you expect to see thousands of neutrinos in each dune or hyper-K. As already said, you can trigger the optical telescope with this. And you see the spectrum. It will teach us a lot about neutrinos. As you know, if Betelgeuse, who is nearby, goes off, we'll see many, many more. I think 1 million neutrinos, and our DAQ system will be a bit swamped, but we'll deal with it. So what are astrophysical neutrinos? Well, they come from far, far away. And this sketch, which was made by my colleague Linda, so yeah, I shamelessly stole slides, obviously, shows the principle. Now, protons curve, so you don't know where they come from. Photons get absorbed if there's something in between. Neutrinos, 60 light years of water, you can go a hell of a lot a distance till you go that distance. So they come back. And there is one experiment, I'm going to show a few slides, which is called IceCube. It's also a water Cherenkov experiment of a different kind because it uses frozen water. Effectively, it uses the ice shield of the South Antarctica, which is about 3 kilometers deep. So basically, about 5,000 modules have been inserted, and there's quite some logistics going on to do that. And so, but it is on the South Pole, and it's running, and it has done lots of results yet, and we are still learning. So this is what happens if a particle goes through from above. All the stations light up, and you can reconstruct it. The whole detector is basically a kilometer cubed. This is one which comes from the side. So this is, I believe, a neutrino event. And you can see it. This was done in 2009. They had these very high energy events in the order of 50. And it's not clear what the origin of these events are. So this is a genuine astrophysical question. But it's getting ever so more exciting. One is there are these blazars, which are active galactic nuclei, which basically put out a jet, and they are humongously energetic. And it seems like 13 plus or minus 5 astrophysical neutrinos, which I'm not quite sure, but I believe it's these guys, came within a short time window from this direction. So with IceCube, we now enter what we call multi-messenger astronomy. You all have heard about gravitational waves, and they will expect neutrinos. There is this GW 1708117, which is a multi-messenger event because it was seen as gravitational wave, a gamma ray-based burst and visible light. On the bottom, you see pictures of Virgo, LIGO, and Antares, which was similar to what do you call to IceCube in the Mediterranean. It has a predecessor, which will be called SKA. No, SKA is radio, so it's KM3net. And when neutrinos will be discovered in a multi-messenger event, that will be a spectacular discovery. So, now you all have this friend, and what do you do? Is it any use? What does this do to the GDP? So, what have neutrinos ever done for us? Or do neutrinos have practical applications? Now, I'm really going out on a limb. I mean, I would have laughed at this not too long ago. But actually, nuclear non-proliferation is a serious business. There's a threat, and there are rules, and one of the rules of the game is trust is good, checking is better. While there are, let's call it political hiccups, so wouldn't quite work that well with Iran at the moment, but you want to make sure that you understand what other countries are doing. Now, any nuclear reactor above ground, you can see the thermal footprint, and it's known. If you put it underground, you can hide it. But if you produce nuclear reactions, you cannot hide the neutrinos. They'll go. So can you detect the neutrinos? And there is a project called AIT, Advanced Instrumentation Testbed, together with the Watchman collaboration, jointly UK and US. And the idea is build a water Cherenkov detector, use this inverse beta decay reaction, and try to detect the neutron as well. And you can do this if you put something with gadolinium, which has a terribly high interaction cross-section, into the water. And so you get a delayed signal, which is used to remove backgrounds. Now, where would you do that? Actually, Bulby Mine is 25 kilometers from Hartlepool nuclear reactor. It has an underground science laboratory already. Dark matter experiments have been done there. So it's the perfect spot. So what we are going to build is actually the largest particle physics experiment in the UK for a generation and put it down will be mine. And yeah, I thought I better show what we are doing. So we are basically testing these 10-inch photo tubes. And yeah, a silly picture is always good to end or coming close to the end. I think I'm at the end. Yeah, just as a summary, neutrinos, because they have so many surprises, they tend to lead to surprises. They tend to lead to prizes. And I predict there will be more depending what's happening. So let me conclude. Neutrinos are fascinating. Not only crime story, but we know things well, like neutrino oscillation, neutrino mass, but we still don't know this mass hierarchy. And neutrinos will play an increasing role in particle astrophysics. And neutrino can be useful. I forgot to say, there are some sci-fi people dreaming about using neutrino to discuss with people in far galaxies. I've also seen someone who wanted to use neutrinos to talk to a submarine, which is somewhere under the North Pole, which cannot switch on its engine for obvious reason. Okay, I better stop here. Probably have taken too much of your time.
Well, thank you very, very much, Professor. It was absolutely fascinating. Some of the physics was a bit stretching for me, but we have a broad spectrum in the society, and others will have grasped some of those far more easily. It never ceases to amaze me that some of the smallest things we ever know about in the universe have the largest impact. And the neutrinos seem to be one of those. Questions? Anything, Peter?
Yes. Well, Sean, you were looking for a piece of clarification on the speed of light through various mediums.
Yes, it was just, and firstly, Professor, thank you for an absolutely fascinating presentation. It was when you were speaking earlier in one of your slides, I think you referred to Cherenkov light, and I think if I remember what you said was that neutrinos were emitted by charged particles traveling faster than the speed of light through a medium. Were you talking about the speed of light through the Earth's atmosphere? Because I presume that would be slower than the maximum speed of light through a vacuum.
No, let me see if I can find the slide quickly. Where was I?
Yeah, that's it.
Yeah, no, this is in the supernovae detector in water. So what happens is, and you can see it here essentially, a neutrino comes in, produces an electron or a muon, so a charged particle in the water.
Yeah.
Water has a fairly high refractive index, 1.33. So if it's faster than 2/3 the speed of light, it will start producing Cherenkov light. So this is the same. That's why you see this blue glow on the water shield in a nuclear reactor.
I see. Thank you.
You're welcome.
Okay. Andrew was asking if detection is always in liquids. Andrew, is your microphone working today?
Working today? You switched it on. Can you hear me?
Yes.
Yes.
Yes. Yes. Before this evening, my total knowledge about neutrinos came from a Royal Institution Christmas lecture given by Edinburgh's own Malcolm Lawyer. And he had a tank of something and the detector, and every so often there'd be a ping, and he was, oh, another neutrino. So, you know, you started with cleaning fluid and end up with liquid argon and now water. So that seems to be the key, yes?
That's not necessarily the case. Basically, you cannot detect the neutrino itself, or you only detect it when it produces something. And the something you can do in many ways.
In many ways.
one of them is, and now we have an echo, probably you have to turn
Sorry,
on.
can I, Andrew, can you turn your
He has,
microphone
now
off,
it's fine.
please?
So basically, if you're in water, if you have something which is transparent, you can do it with Cherenkov light. In liquid argon, we use this time projection chamber system where there it's the electrons which drift. But in ice cube, it's also the transparency of the ice, so it's optical. So it can be optical, but it doesn't have to be. There are near detectors. There's now a proposal to use high pressure gas as a near detector for dune. In principle, any medium works. There are NOVA, which is an experiment like T2K that I didn't have time to talk about. Basically, you and Minos basically used plastic scintillator. So any material which can be used to build a particle physics detector can be used to build a neutrino detector as well.
Thank
I
you.
hope that
Thank you
helps.
for that. Carl has a question. Are you there, Carl?
I am. Thank you very much for an excellent talk. I was wondering, or we were wondering, if how the neutrino signal was received before the optical signal in a supernova. From a supernova 1987A, you said that the neutrino signal was received a couple of hours before the optical counterpart.
I'm not a supernova specialist. The way I understand is that neutrinos, once they're created, they go on their way. Yeah? So they measure the time of the supernova. For the light to get out, it has to get out of the material, and that can take time. There's another more extreme example, which is our sun. I don't know if you have heard this. The neutrinos we see from the sun are the ones as they were generated 8 minutes ago, because it takes 8 minutes for them to get here. The photons, which hopefully gonna light up Edinburgh sky tomorrow so that I can go cycling, have been created 300,000 years ago, because it takes that long for a photon created at the center of the sun where the fusion takes place till it makes its way out. Now for a supernova, it goes a bit faster, but it's not instantaneously. You are muted.
Microphone.
Sorry, thank you very much. That makes a lot of sense. That's a really good explanation. Thank you.
You're welcome.
There's one from YouTube here, Robert Baker. Could one use Enceladus as a detector?
Could one use?
Enceladus, the moon, I presume.
Well, the moon is usually a nuisance for astronomy.
This is the moon of Saturn, so it's a liquid moon.
I would have to look up how transparent, if it's transparent, if it's the problem with, if you take just any object, it will likely be too noisy. But the idea is actually good. It's being used in, amongst others, these double beta decay experiments. They use what we call bolometers, where basically they take something and they measure the temperature. And when a neutrino causes a reaction, the disturbs the lattice. So the technical term is phonons, and these phonons get propagated and increase the temperature. You can imagine that this has to be under very controlled and background-free environment, and I'm afraid Enceladus probably won't do, but yeah, write a paper, submit it to the archive, and you'll find out what it's worth.
Good point.
Is that all the questions, Peter?
That's all the ones I've got here at the moment.
Well, could we thank Professor Muheim in the usual way then? Thank you very much.
Welcome.
Thank you very much indeed. Okay, I think we need to hand back control. I think it's Horst next, who's going to talk to us about the sky in May.
Okay, how's my sound? Can anyone hear me?
Yep.
Yes, I can.
Okay. Takes a few seconds to share with, no, it takes only 1 second to share. So I hope the first slide is up now.
Yes.
And what do we do with this gadget? Okay, so the sky in May 2020. As usual, I will start with a look at the evening sky at dusk towards the northwest. Hang on here. So here's northwest. Hang on, I'm just getting a warning about CPU usage. I will have to do something about that. Because I'm actually somewhere folding proteins. Which interferes with what else the computer wants to do. Well, at least you can all see what's going on here. Right. So the sky looking to the northwest, when the sun is about 6 degrees below the horizon, what we call civil twilight. And in the evening sky, as we all know, there's Venus starting out here today with a brightness of -4.5, very bright naturally, and a diameter of 39 arc seconds. But Venus will continue to drop lower and lower in the sky, and it will eventually disappear here on the 28th, being somewhat fainter at -4.0, which is still very bright, of course. And it will be larger, it will be almost an arc minute in size, in diameter. This is because the planets, the inner planets, Venus and Mercury in the west, they are coming towards us, so they will grow in size, and the crescents will become thinner as this happens. Mercury also makes an appearance. It should pop up on the 11th of May, quite bright at -1.6. Quite small in comparison, of course, at 5 arc seconds, and it will pop out. These dots are in 2-day intervals, by the way. So it will come up over about 2 weeks and reach the highest point here around the 26th, when it is easiest visible. Still -0.2 magnitude and a bit larger already. And then it drops down again, basically backtracks where it came from. And so by the end, after 6 weeks, from today, it will still be approaching the horizon, but it will then be twice as large as when it popped up. So that's the evening sky, doing the same for the morning sky. Here, I'm not looking at northeast, but at southeast. That is because these are not really twilight planets. They are supposedly at night, but it doesn't really get night. And by the time these planets are high enough above the horizon to be worth looking at them, it is already twilight. So we have the three other planets here. Mars. Mars is the odd one out here because it is moving to the left and upwards. It is also growing in size a little bit, and is getting brighter from plus 0.4 to minus 0.2. The other two, Saturn is the one on the left, and Jupiter is the brighter one on the right. So they start out here at about 10 degrees altitude and get a little bit higher, but that is mostly because they get towards the highest point in the south. And so Jupiter, quite bright at minus 2.3. At the start, larger than Venus. At the end, not as large as Venus is by then. But it brightens also to minus 2.6. And Saturn, quite similarly, it gets a bit larger and it gets brighter. And then next I have, as usually, the comparison of what they might look like in the telescope. These are all to the same scale. Mercury quite small, Venus quite large, and you can hardly see here, this is it. And there's the crescent, a very thin sliver by the time it drops down to the horizon on the 28th. Mars, quite small. Jupiter, usually I say, most months I say Jupiter is the largest of the planets, but this time Venus manages to overtake it. Jupiter being around 45 arc seconds, say. Saturn, if you include the ring, it's a similar size as Jupiter. You may have noticed that the tracks in the evening sky of Venus and Mercury meet somewhere. Now, it's not always the case that where the tracks cross, both will also be at the same time, and it's not quite the case. This is the view on the 21st, when Mercury is 1 or 1.5 degrees below Venus, and on the next day, on the 22nd, Venus has dropped down and Mercury is to the left of Venus. But both days it should be very, very easy to find Mercury once you have found Venus. Although I don't know, it may be quite easy to find Mercury anyway. You just have to go out and try and experience yourself. With that, that's the planets. Now I'm moving on to the night sky, such as there is night. So I'm looking here west. These are the times when the chart is valid. So in the middle of the month, it's at 11 o'clock. At the start of the month, you have to wait an hour longer. At the end of the month, you would have to come out an hour earlier to see the same stars in the same place. So here in the west, we still see Venus up here, and it's actually quite close to this star, which belongs to Taurus, but is one of the 5 that make up Auriga. And to the left of it is the constellation Gemini or Gemini or Gemini. The twins, Castor and Pollux, I don't know which is which. And over here we have also quite recognizable Leo, the lion here, the head of the lion and the body of the lion. And its paw here is the bright star Regulus, which is exactly on the, almost exactly on the ecliptic, which is the blue line here. In terms of objects to look at, I would recommend the Beehive cluster here, which is in the constellation of Cancer, which I have not drawn. It's quite hard to recognize, it's quite faint stars, but just knowing that you're looking for a bright open cluster between these two constellations with binoculars will be enough to find it. Other famous objects are M81 and M82, the two galaxies up here in Ursa Major. This is the Big Dipper, this is the bowl of the Big Dipper. The handle is above the margin of the screen. So Ursa Major is in the zenith, right above us. Okay, so that's the view west. If we now look to the south, there's Leo again. Due south is Virgo, the next constellation on the ecliptic, with the bright star Spica. And up here we have another bright star, Arcturus, which belongs to Bootes. And if you could see Ursa Major, then Alan Pickup would say that the arch of the Big Dipper arches down and points exactly to Arcturus, and then you can follow that arc and find Spica. There are two small constellations I want to mention. Here's Corona Borealis, the northern crown, is small but quite recognizable. And these four stars, or the fifth one down here, that is quite a easily recognizable asterism, even though the stars are quite faint. And this is Corvus, the crow. And it's perhaps interesting because the Sombrero Nebula, the galaxy, is somewhere around here. Maybe that one, I'm not sure. And I should mention the Leo triplet, three galaxies almost in the same field of view down here. Well, up here. Melot 111 is an open star cluster. It's this one. It's the huge grouping of stars that you see there, and it's the main feature of the constellation Coma. And down here, I don't know whether you can see that there are a lot of red dots here. These are galaxies in the galaxy clusters of Virgo and Coma. So that is looking south. If I move on to the east, in the east there's the Northern Crown again. Over here, quite recognizable is Lyra, a small but very recognizable constellation because the very bright star Vega is in it. And then here we have Cygnus, the swan or the Northern Cross. This is the tail of Cygnus, its bright star Deneb. And this is the head. Albireo is a famous double star with two quite different colors, and the wings. Here, not so easy to find, but quite important, is the constellation of Hercules. So we're looking for these four stars, and then you take this side and you go 2/3 up, and then you find M13, the very famous globular cluster. There's another globular cluster, M92, not far away. I think it is this one. Another globular cluster is in Lyra over here, M56. But there's also, of course, the Ring Nebula in Lyra, which is very close to the center between these two stars. And I've noted here Epsilon Lyrae is a star. It's this one here. And if you have very, very good eyesight, you can see that it's a double star, even with the naked eye. Well, I never quite managed, I must say. And if you use a telescope, if you use a 6 or 8-inch telescope, then you may be able to see that each of the two stars is again a double star with 2 arcseconds separation. So this Epsilon Lyrae is a test both for your naked eye and for your telescope. I've listed the North American Nebula, but this is probably not the best time of year to look for it here next to Deneb. You have to think that in August, these stars will be further along. They will be in the south and southwest and much higher above the horizon. I should mention, though, down here Scorpio, because Scorpio is hard to see at any time, because it is visible only very briefly above the horizon. And it's quite, these three stars are quite recognizable when you see them low on the southern horizon. And finally, Aquila, I have to mention, and the bright star Altair, because these three stars form the summer triangle, Altair, Vega, and Deneb. So yes, with summer soon arriving, it's time that the summer triangle should be rising in the east. Okay, so that's it for the night sky. Well, for the stars, but there are some comments about, and I have drawn this chart. This is just a star chart. It's not in terms of the horizon. And so here's the pole of the celestial pole, Polaris, and here's the ecliptic, and down here is the equator. Two of these comets we are already sort of familiar with, 2017 T2 moves in this direction fairly steadily. These are also two-day time intervals, these dots. So over those 6 weeks, it moves from a very faint constellation called Camelopardalis, or giraffe, into the Big Dipper. This is again the ball of the Big Dipper over here. And the imaging group have taken pictures of this comet already. Is that the one yes, I think that's the one I took, in fact. Whereas Ian Smith, I know, had a picture of this one, 2019 Y4, which also is in Camelopardalis, so in a similar region of the sky, but it is moving the other way. It is going down, and it is speeding up, which is a sign that it's getting closer to the sun and to the Earth. And I should have said, brightness estimates very roughly for T2 is about 8.3, but these can be very wrong. It can be wrong by several magnitudes. So in that sense, Y4 getting to 2.5 magnitude is perhaps unlikely, especially since it's broken up into pieces. On the other hand, more pieces may be more outgassing and may make more light. It's hard to know, but that's why they're comets, so that you watch and see what actually happens. So at its brightest, it would be here, which looks quite close to the sun, but a short while before, it should be possible to see it at night, because this is essentially the northern sky. You can see these things over the northern horizon all night long. And there's a third comet coming along, which was discovered this year, 2020 F8, which is currently down here in Aquarius or Cetus, the Oarfish, I'm not sure. And it's moving fast, and then slows down, and it will be brightest up here when it is in Perseus on the 21st. And it will then move on over here. It starts at about 8th magnitude, and it will end at about 8th. And its peak, not terribly bright, but it is still, with a telescope or binoculars, it should be possible to see it. And certainly for the images, it's something to look out for. So I've drawn here where the sun is at the end of May, so that you get an idea of how close or how disturbing the sun will be in finding Y4. Now I've forgotten what comes next. So next comes, of course, noctilucent cloud, hopefully. This I have to talk about every year, of course, because these are clouds that are bright at night time. And what is happening is we're looking during twilight, when the sun is between 4 and 16 degrees below the horizon. And we look north, where the sun is behind the horizon. And we look between late May and early August. That's when these clouds appear. And what's physically happening, these are at 82 kilometers altitude, where there's still sunlight, whereas for us it is darkness, more or less. And this is the coldest layer of the atmosphere, which is called the mesopause. And in summer it is colder than at other times of the year. Don't ask me why, but that is how it is. There are people, I think, who don't understand why that is the case. Of course, at that altitude, the air is very, very thin, and water vapor has difficulty to get above 10 kilometers altitude, so it is even thinner. So it's almost a miracle that these things can actually form, and it is in summer it is just cold enough for the water vapor to freeze out. But it does need seeds to freeze out on, and that's where probably meteoric dust comes in, which always comes down from space into the atmosphere. These clouds are tied to global warming. They were not observed before the Industrial Revolution really increased the CO levels. Well, today we can measure it, but at the time we wouldn't have been able to measure. So late 19th century was the first time they were observed. And they have become stronger and more frequent as the CO levels rose in the atmosphere. So in a good year, you can expect that there's some sort of a display of noctilucent cloud every other clear night. Okay, so I've already moved on to a sample of the images from the Flickr group, from the imaging group. Chronologically, I will be first because after the last meeting on the 3rd, where Alan told us that Venus is passing next to the Pleiades, I went out and took the picture to check. And as you can see, I had a bit of luck with the cloud. Chronologically, next is Peter's image of the moon, an almost full moon, but not quite. There's quite a bit of shadow and detail to be seen on the rim there. And I mentioned this, Ian Smith took a picture of the comet Y4, and he timed it very well because there was a meteor coming through the field as well. So well done, Ian. I mentioned these two, the galaxies M81 and M82. This is a spiral galaxy, half face on. This is edge on, but also an irregular galaxy with an exploding center. And this picture was taken by Nigel Goodman. This picture is by Mark Phillips, M101, the pinwheel galaxy. And I say 19-ish because he emphasizes that it took him 3 sessions to get all the data. So I presume that is 3 nights. And here Andrew Farrow's M3 globular cluster in Bootes, which I forgot to point out in the night charts. And this one is by Mark McGovern. He has a name for it, which I haven't been aware of, Macarian's chain, which I presume is this string of galaxies here. That's the galaxy. Those are quite large galaxies, but there are many more. There's one. Can I find a really obscure one? No. This one down here is M87, and I think I can possibly see the jet coming out of it, but I would have to check whether that is bright enough to be seen. So in fact, this is a picture of a black hole, because since last year we know that at the center of M87 there is a black hole that has been imaged by the sub-millimeter telescopes of the world. And that's it from me. Anyone still there?
Thank you. Thank you.
It's strange when there's absolutely no feedback.
Yes, it takes getting used to. Well, thank you very much, Horst.
Yes.
Mark, can we have a slide back? Oh, it was there and now it's gone. I think Mark's internet is not running the fastest tonight. Thank you. Well, thank you, Horst. Thank you, everybody, for this evening. I'll just leave this slide up about the forthcoming events. As we said, there's the ROE on Monday, but I think you'll have to join via Eventbrite, but hopefully we'll be able to put a link through. The imaging group is on Wednesday. A reminder to council members, we have a council meeting on Tuesday. On Friday, we have the exciting interaction with Tosh, and you can see the rest. So thank you very much, everybody. Stay safe, and I'll probably see quite a few of you on Wednesday. Thank you now. Good night.